Langevin dynamics and using a perturbed measure. And that is also kind of in line maybe with how the history of the subject came about. I think one of Yang Song's first papers that actually got this to work was within this Langevin setting. And then people kind of realized, well, you can kind of flip things around and then make an SD out of them. So I'm going to stick to the Langevin setting today, but I'll give some connections to the SD setting. And that will be in this first paper, which is with Ricardo, who's here, as well as, so Ricardo is at Caltech, as well as Jay Lim, who was an intern at NVIDIA and is currently doing a PhD at Mila. The second part of this talk will relate how I use some of these ideas to do maybe some video generation, and in particular video generation with image models. So I'm going to just take a model which can only generate images, and I'm going to try to adapt it in some way so that I can actually generate temporally consistent videos. Okay, that will be the idea. And this is some work with Giannis Daras, who is doing a PhD at UT Austin and was an intern at NVIDIA, as well as mainly Arash Vagdad, who is also at NVIDIA. Okay, so let me maybe get started on the first part, which will be just this function space kind of perspective or infinite dimensional perspective on diffusion models. So I think, generally yesterday, I think Andrew gave a fantastic introduction to the Church of Infinite Dimensions, and I subscribe to it. So I'm not going to try and do too much. Maybe I'll just tell you a little bit of why, for this particular setting, that point of view will be useful. Okay, I'll mostly focus. So of course, there's tons of possible applications for generative modeling. We've seen many of them throughout the workshop. Some of them being in science. My main focus will be maybe on imaging today, at least in terms of application. And why would you maybe care about working in this infinite dimensional setting at all? So one of the maybe biggest benefits, I would say, is being able to generate images at kind of any resolution. So if I think of images as functions, then the idea would be to be able to generate images at any resolution at a fixed kind of sampling cost, right? So when I say fixed sampling cost, what I really mean here is the number of steps that I discretize my process with that it has to take. So regardless that, I do not want that to depend on the resolution. So I don't want that to depend on the dimension of the problem. If I want, if I want to generate very, very high quality images, I can do that by just taking, say, 200 steps, and that's it. Okay, so that's really the main motivation for doing this. There's others, so you could also incorporate, images of all kinds of resolutions within your data set, and that can help you learn this problem. This is something that I would say has really not been explored in the imaging literature almost at all, and I think it's a very good direction to try and go in. And then the other one, which will be kind of maybe the main thrust of my application today, will be continuous editing of images. So if my noise is at least a continuous function or something that I can make sense of pointwise, then I can edit that thing in this pointwise way and try to get out images which have been similarly edited. Okay, so that'll be the basic idea. Okay, so in the first part of the talk, at least, or generally throughout, there will be a lot of notation. So I really apologize for that. I'll do my best to kind of maybe explain it and go slowly. Okay, so this we've all seen today and throughout last month. But my goal will be this. I'll have some measure. So my data measure will always be denoted by mu. And I'll assume that data measure is supported on a space U. So the space U can be some infinite dimensional space. Soon it will be a separable Hilbert space. Okay. And what I'm given is going to be data samples from U, and they'll be IID, and I'll denote those usually by U, and I'll assume to have n of them. Okay. And that's the only knowledge that I'm going to assume to have of this measure mu. Okay. My goal will now be to find a transport map. Okay. It will be to find a transport map that, given some other measure, which I will denote by nu. So mu and nu. If I mess up saying those, I'm sorry. Correct me. And so my goal will be to find such a transport map, and this transport map will be defined in some way. And I'm going to allow this transport map to even define a coupling, so to be stochastic, if you want. Okay. So this is the general notation of the problem. I have a reference measure nu, a data measure mu, and I want to sample from my data measure knowing only samples, and that's it. Okay. There's also the same kind of setting which you can make conditional. So if your data measure can be conditioned on some other, say, variable y, then you can kind of set up the same exact problem. And in fact, in application, especially for videos, I will be mostly interested in the conditional setting, but my notation will suppress it. So everything I show you will be in this unconditional setting. Really, I'll be working in this conditional setting, and I'll try to make clear when I'm working in this conditional setting. Okay. All right. So of course, there's tons of different approaches that have come out now for how to solve this problem. And the one I'm going to focus today is diffusion models. Okay. Okay. So let's get started with the infinite dimensional setting. Okay. So like I said, my goal is to sample from this measure mu. But I'll say that that problem is too hard. So all I know about mu is that I have some samples from it. And to me, that problem is just too difficult. So I'll instead try and relax it a little bit. And I'll relax it by slightly perturbing the measure mu. Okay. So let's just go through notation because I want to set it up. So my data space U will be a Hilbert space H. My reference space X, which should be V, I'm sorry, is also H. And they're going to be an infinite dimensional Hilbert space. So the reason I work in a Hilbert space, not a Banach space, will become clear later. It just makes some calculations that we need explicitly much easier. Okay. So I'll restrict myself to Hilbert space for now. Okay. So like I said, I think the problem of sampling mu is too hard. So I pick instead something to perturb it with. And what I'm going to perturb it with in particular is going to be a centered Gaussian. Okay, because that's kind of a simple thing that we understand and can maybe work with. Okay, so I pick some parameter sigma and some trace class covariance C. Okay, and the fact of it being trace class will be important because that will actually give us functions rather than distributions, and then we can actually maybe approximate things. Okay, I can say more to that point later. So C is the covariance of my perturbing measure. And then I'll make an assumption. And this is going to be a crucial assumption that I use throughout this talk. And the assumption is that my data measure charges the Cameron-Martin space of my perturbed measure. In particular, what this says is that the support of this data measure is smoother than the noise with which I'm perturbing it. Okay, and I'll quantify exactly how much smoother I need it to be. Okay, so this assumption will really make the rest of this theory work. And it is a sufficient condition to make this theory work. I don't know if it's a necessary condition to make this theory work. And I think that's a very interesting kind of open question. I think some of the work by Yakil also shows that he has similar results, which also need this instead for the reversibility of DSD. No, okay, maybe not. We can talk. Okay, so my target measure now that I'm going to sample from is going to be mu sigma, and I'm going to want a notion of a score. So we're going to do diffusion models. So I want a score. And how do I get a score? Well, to get a score, I need a density. And so I need to pick some other measure with which my mu sigma will be at least absolutely continuous with it, but we'll need equivalence, in fact, to make this work. And a very natural choice for this other measure is, in fact, the perturbing measure itself. Okay. And it turns out that you can indeed get this equivalence. I'll show this on the next slide. It's a very easy result. Okay. And of course, you know, in some maybe Wasserstein metric, these two are not too far apart. So solving the problem of sampling from mu sigma maybe is not such a bad idea than straightforward sampling from mu. Okay. So let me I'll just give a slightly more general statement of this equivalence. It will really be the same. So I slightly changed notation here. So I do want to just make that a point, and maybe it's a bad idea, don't know. So again, mu is my data measure, mu is my perturbing measure, okay? And now so here there's no sigma. So I've dropped the sigma parameter, and instead I'm putting a tilde. So this is just to make a more general statement. That's all. Okay, and I'm considering, of course, the convolution of the two, which is the perturbation. Okay, and I'm also going to write mu tilde u with a u for the conditional of v given u. So if this map kind of defines coordinates, which is this one. And so you can, for every single u, you may consider this conditional. Okay, and this is the notation I'm going to use for conditionals by putting an upper script. Okay. So what I have is a very simple result, which, so the first part of this follows from the Cameron-Martin theorem, essentially, that if my perturbing measure is indeed a Gaussian, and I had that my data measure charges its Cameron-Martin space, then the two are equivalent. So one thing to note is that the data measure will never be equivalent to the perturbing measure given this condition. So if I have this condition, the data measure cannot possibly ever be equivalent to the perturbing measure. Because they just have different supports. This lives on a smoother space, right? But it will be equivalent to the perturbed one. And moreover, I have that for every single conditional, every single of the perturbed measure is also equivalent to my perturbing. Okay, so both of these will be crucial. The first one is crucial in obtaining a density that we need. The second one will be crucial in obtaining what I call denoising score matching, which we'll see in a second. Okay, so I hope this is okay. So now that we have this, I'll go back to my sigma notation. And so now that we have equivalence of measure, I can just apply Radon-Nikodym theorem to get a density. And in particular, because I have equivalence of the measures, I know that this density will be strictly positive. And because it's strictly positive, it means I can write it in terms of the exponential of potential function. Okay, so I can extract out of this potential, which I'm calling here phi sigma. And an assumption now that I'm going to make, which to me is still unclear how that relates to an assumption on the data measure itself. So this is a gap in the theory, at least for me, is that I will need to assume that this potential, phi sigma, is Fréchet differentiable along the Cameron-Martin space of the perturbation. Okay, so if the data measure was a Gaussian, which satisfied my condition, then this actually will be satisfied. So this is true. So if my data measure is a Gaussian, this is fine. But in general, I don't have a good set of conditions on my data measure to make this true. Okay, so I'm just going to assume it for now. Okay. Once I have this, then now I can define a score, right? Because I have the score will simply be the log of the density, which is nothing but the potential, and then differentiate it along the Cameron-Martin space. Right? Okay. So now I can get a score, or a logarithmic derivative, sometimes called, which is a mapping from my space H into what's the topological dual of the Cameron-Martin space. Okay. So this in some sense is a pretty bad space, right? Because so H naught is the Cameron-Martin space of my perturbing Gaussian, which is relatively smooth. So if I take a dual of that's a very rough space. Okay, so this is in some sense a pretty bad mapping, from the point of view of approximation at least. So what we would want ideally is actually a nicer mapping, and it turns out for sampling you can get away with getting a nicer mapping. Okay, so what you can do is actually precondition this mapping and make it a map from H to H naught, and then use that within the Langevin equation, and that's enough. Okay, so what I call here denoising score matching is now the idea of how do I get at such a quantity, and so this is the quantity I want to get. So this is phi sigma differentiated in the direction of H naught, preconditioned by C and sigma squared. So the sigma squared doesn't really matter; it's just a scalar parameter. The C is what makes this a mapping from H naught star into H naught. Okay, and it turns out, and I'll show a general result of how one derives this, that you can find this mapping, or at least you can set up an optimization problem, which is tractable, which is what's called denoising score matching, as follows to find this. So this says I take the expected value over all my data points, and then over all my perturbing Gaussians, and I try to denoise. So this is the V here would be a noisy version of my data point. The U would be the data point itself. And then, of course, because we're working in with something correlated, we will in fact pick up this one. Okay, so this is a calculation which comes out of the following kind of more general result on denoising. So you can do denoising, denoising score matching in a much more general way. And that's what I want to show next. So again, this slide is very busy, which I apologize for. So I'm just trying to go through it very slowly. Okay. So I want to give the reason it's busy is because I want to give a very general statement to when you can do denoising score matching. Okay. So I'm still working in this Hilbert space setting, and I'll take E to be a continuously embedded Hilbert space within H. Okay. And so the E is essentially the H naught of the previous slide. Okay. Now I'll take my perturbing measure, which used to be mu sigma. Now they know mu tilde because there's no sigma parameter. And I'll allow it to be anything. So I'll allow it to be the push forward. So if this was to be a convolution, then this map T would just be the sum, right? But I'll actually here allow this map to be anything. I need to make no assumptions with this map apart from it being measurable, so that this push forward makes sense. Okay. And again, I'll use this tilde U notation to denote the conditionals. Okay. And now the assumption that I need to make is that there's some other probability measure here now nu naught. This needs to be, so this was mu sigma before. Now it's just nu naught because there's no sigma parameter in this statement. Okay. To which my perturbed measure is equivalent, to which all the conditionals are also equivalent. Okay. So this is to get density. Okay. So now I can get density with respect to this new measure for both my things. And I'm going to assume that they're Efreche differentiable, so along the directions of E. Okay. And then I'll only make one more assumption, which is that they're square integrable. Okay. So the scores, to define a score, you need differentiability. And then I'll assume that the scores themselves are also square integrable. Okay. And that's it. So given this assumption, if I define any family of parametric mappings, which map from H to E star, and I assume that for all parameters theta, these are also square integrable, then I can show that trying to match the score. So this is the loss function that one would usually want to solve, right? So this is G here wants to be the score that I learned. DE phi is simply just the score. Of course, we don't actually know the score. We only have data samples, so we can never get at this directly. But what you can show is that that is equivalent to what will be the denoising score matching, which is this conditional. So you can get at this conditional here under basically almost no assumptions, so incredibly general assumptions. Okay, and because we're working, so because in the previous setting, this conditional was one of a Gaussian, and we're working in a Hilbert space setting, we can actually compute, and that brings back, and this is how this loss function actually arises. Okay, so I hope that's clear. Okay. Okay, good. So now that I have a score, or at least I have some notion of how to find the score, I can actually optimize. Then I can now plug this into a Langevin equation and try and actually sample, given I've learned this score. Okay, so this is well known. This is of the work of Andrew, this precondition Langevin equation here, where so now I'm using X to denote the trajectories of the Langevin equation. I know a lot of notation. I'm sorry. And Z will be a sigma squared C Wiener process, so adapted to the function space. So if I just start, so if I know this, I've learned this, then I can just start this anywhere, run it for some indefinite amount of time, and I should get a sample out of mu sigma, which is the measure that I'm after, right? Okay. So just a practical note on this, and what people usually do in practice is that people don't usually go after this quantity. They go after this entire quantity together. So you can do that. You can simply say, instead of learning this, I'm going to learn this with the identity. And then you can see how that affects your loss function. So that it's just a reparameterization. And the reason people like to do that in some sense is because instead of predicting the data, just smooth relative to the noise, they want to predict the noise. So they want to have a neural network which tries to predict the noise. Because this way, if you're trying to predict something rougher, ultimately you're doing something like an L2 loss, and that will smooth. And so if the thing you're going after is very rough already, this smoothing doesn't hurt you as much. Rather, if you're trying to go already against the thing you're after, and that smoothing will in fact hurt you. Okay, so this is something just people like to do in practice. And you can optimize for this quantity instead, and then of course discretize your Langevin. Okay. Okay. And now I have in my transport map language, which will be more useful later than it is now, I have that if I start anywhere, and I simply, so psi here now is the flow map associated to the solution of this SD. If I start anywhere and I run it up to time tau, then I can hope that this is a sample from mu sigma. Okay, and a fixed tau. So why is this maybe kind of a terrible thing to do? So I've described the process for sampling mu sigma, but perhaps it's not the best thing to do. So I would say there's two reasons why maybe it's not the best thing to do. One is because this Langevin dynamic can have a very bad mixing time. So if this is multimodal, the amount of time I actually need to run it to really guarantee that it's a good sample may be very, 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 very long. Okay. Number two, the way I've set up this problem, I've only learned the score near where I have data, right? Because if I look at how I discretize this, so mu is just, so, I mean, in reality, mu is a Dirac, or is a sum of Diracs, right? Because I really only have data. That's what I get at. So a sample from this is essentially a little bit of Gaussian spread between Dirac. Okay? So if I do this optimization, even if I do this optimization really, really, really well, I really will have only seen data, like I really will have only seen points around my data points. And so outside of that, this mapping, I cannot hope for it to be accurate, right?
Let me understand that the difference with finite dimensional case now. Really, you inject your noise once in estimation. Where in the finite dimensional you inject many times in turn.
All right, so I haven't gotten there yet. Okay. Yeah. Right. So that's how we're gonna fix it. so yeah.
So just in practice, how you represent, because U is a function, so you represent it. It's like you discretize it, or you represent it as a sum of splines or
sure,
something like that.
Oh, when I actually go to discretize it. So when I actually go to discretize it, U will usually be given to me on a grid. And what I'll need to do is I'll need to treat F in an appropriate way so that F can deal with functions at any resolution, regardless of the grid that I'm given.
So you have discretization, so you have to discretize U and you have to discretize types at the end.
Yes, there are. Yes. And here I'm not really going to be concerned with discretizing time. So everything is going to be already kind of in discrete time. Okay. Yeah. Okay. This is okay. Right. So I mean, you hit the nail on the head, right? So precisely the way we deal with this issue is by adding more noise at different scales. So you can precisely do that, which is just kind of warm start Langevin, right? If you will. So this is a notationally cumbersome slide to say we do warm start Langevin, right? So instead of just doing a single sigma, I pick a whole set of scales for sigma, and now I learn the score at each of these scales. And then I hope now that if I start anywhere and I just, initialize each of my Langevin dynamics at the place where my previous one stops, then I should be okay. Yeah.
Yeah, there's a little bit of worry here for me.
Yeah.
Because this is in the infinite dimensional.
Sure.
And you have to project to the finite dimensional its time, right? Because in order to do the approximation, you cannot do it in the infinite dimensional. And now,
which approximation?
Because you are infinite dimensional, right?
Yes.
So in practice, I will take only a finite dimensional approximation, whatever is your favorite kind of approximation.
Yes.
For infinite dimensional objects.
Yes.
And then every time now I pick the injection of noise,
yes,
I have to keep track also of this kind of error. Every time I have a finite dimensional system.
You mean because the noise you realize will ultimately be finite dimensional because that's the only thing you can realize. Sure, I agree. Yes. So you could potentially try to add noise at different kind of the increasing scale of, trying to get more and more different space. So if I do this, say, by some scale extension, then I could try to maybe add more and more terms to it as I do that. Yeah. Okay. So, and now I have a transport map, which I'll call psi, unfortunate notation, which will be just the composition of all these Langevin dynamics together. Okay, started and stopped. Okay, so this will be kind of the map I work with, hopefully for the rest of the talk. Okay, good. I do want to slightly connect this to the SD perspective because there has been a lot of SD talks given. And the idea of the SD perspective is just to let sigma vary continuously, right? So kind of. So in what I presented, the Gaussian kind of lies out at infinity. Or rather, sorry, our data measure, the thing we want to sample, lies out at infinity. And at 0, there's this Gaussian that we just sample from. In this forward reverse kind of idea, we just swap that. So we take our data, we put it at 0, and then we put out our Gaussian actually out at infinity. And then we take sigma to be kind of infinitesimally small. Okay, that's the basic idea. And if you want to do that kind of in a proper infinite dimensional way, maybe the right object to go after is this conditional expectation here, right? So because you really don't need anything to kind of, this will exist no matter what you do. And the question really you want to ask is, when is this reversible? And I hope Jaak will answer some of these questions for you. I'm not going to try to do that. Okay. Okay, so I do want to say maybe something about the regularity of the noise, because we did have this condition that your perturbation should charge the Cameron-Martin space of, sorry, your data should charge the Cameron-Martin space of the perturbation. And so kind of what does that mean if we take a very, very simple example? So what it means is that, so let's say H here is just L2 on the torus, homogeneous. And we pick our data measure to be Gaussian with some covariance C1. And then we pick our perturbing measure to also be Gaussian with some covariance C2, which there is no square here. And I also give those precise precise definitions, and in fact they'll be minus the Laplacian to some power alpha. Okay, both of them alpha and alpha 1. And I'll assume kind of for good measure, so things that are continuous, that alpha 1 and alpha 2 are greater than d over 2. Okay, and then we can ask in this setting, when does mu charge the Cameron-Martin space of mu sigma? Okay, and the answer is this happens if and only if, we prove that, alpha 1 minus alpha 2 is greater than d over 2. So this means that the data, your data, has to be at least d over 2 smoother than the noise together for this kind of to make any sense. Right? Okay, so I think this is quite nice. It tells you at least something of how you should be picking. And in fact, in practice, people have found them picking less regular noise. So working with white noise instead, in fact, for images is something that's beneficial. I'll show that it's not needed, but it is something that's generally beneficial. Although if you actually look at, in practice, if you look at spectra of some of the things that are generated, you will see that if you use very rough noise, something like white noise to actually generate things, there will be discrepancies in the spectra of your data and of the things you generate. And in fact, the things you generate will be rougher, but on scales you can't actually see. But you can pick that up if you actually compute spectra. Yeah. So I think it is an important general thing to try to worry about how rough is my noise with regards to my data and what is kind of the optimal thing to pick so that I can both sample and keep things consistent. So the last thing I want to say is maybe something, maybe a way of cheating, and is how to get rid of this assumption. And it's cheating because you can modify the perturbation. So you can, instead of saying, so my perturbation was u plus v, so data plus noise. Okay, well I can also just do something to the data and then add the noise. And if I do something which is smoothing, well then surely I can get rid of this assumption. So it just says that it is somewhat cheating. So if I take some smoothing operator and I apply it to my data before I perturb it, well, if it's smoothing enough and kind of goes to, it also has the sigma parameter and goes to the identity as sigma goes to 0, then I'll get this equivalence without any assumptions, and I kind of don't have to do any. Don't worry. But I'll say maybe this is almost besides the point of this. The idea of this infinite dimensional setting, I think, is more to analyze what would happen and what are good choices for you to make, given that you have functional data and understanding that, as opposed to trying to write down something that was very generic. And then if you do this and you take the heat equation, you also have to invert the heat equation. So that's also really hard. So maybe you don't want to do it. Okay. Okay. So now I hope I've given kind of a somewhat clear overview of this. Now, I just want to show some very simple numerical examples of this working. And then I'll get to videos. Okay. So the first example I want to show of this working is just in the case where you're in 1D, and I consider a Gaussian mixture. Okay. And I consider a Gaussian mixture which is sign on one side and minus sign on the other. Okay, over two. So just like this. Okay. And then around that, I add some perturbations. Okay. So this is this is essentially what all my data looks like. Okay. And then I try to do this process by fixing a class of operators which will approximate this. So all this use the Fourier operator, which Andrew described in his talk yesterday. And what I do is at each sort of training resolution, I retrain this operator to try and find the scores. So I sample data at higher and higher resolutions, but fixed, and then I retrain, and then I test and I see what happens. And what I measure is essentially a moment of the resulting distribution. So I'm not claiming this is maybe the best measure. This is the difference between the average power spectra. So this is some moment that they'll tell me roughly how well I've matched the distribution. Certainly not that I've matched it perfectly. Okay? And what I find is that the only thing I have to do, so if I use noise in my noising process, which is trace class, as opposed to if I use white noise in my noising process, what I see is that basically with trace class noise, I keep the number of, I keep this error fixed. So everything here has the same number of backward steps. So I fix the number of backward steps, I retrain, and I look at what happens. And the error I get is fixed. Versus if I actually use white noise, then that error blows up. Okay? So this is maybe to say that you shouldn't be using white noise if you increase your resolution, because you're making your problem harder and harder and harder. So you'd have to scale your approximation as well, right? So here I'm fixing a mapping and I'm retraining it. If I wanted to maybe use white noise at higher resolutions, then I'll have to increase how well this mapping can approximate things for me, right? So if I want to fix cost, this is telling me that. And then the second example is just a very simple MNIST example, where again, we did this with a Fourier operator. We train it with Gaussian noise, trace class noise, and you kind of try to just sample at different resolutions, and this seems to work relatively okay. And I would benchmark it again against the same method, but with that's GAM based, and it does a little bit better. Okay. One thing I do want to say about FID score here, I guess, is that FID score, even though visually to me, the quality of samples doesn't actually decrease, the FID score does increase as you try and compute it at different resolutions. So I think this is a problem of the FID score, that it is not in fact resolutionally invariant, and one would have to think about different measures and better measures of the yes.
So you're training here once with really smooth noise and once with white noise for MNIST, and you get better results with the smooth noise?
So I'm not showing white noise results here. So roughly, if you train at a fixed resolution, the white noise and smooth noise results are roughly the same. But if you keep increasing the resolution, the white noise results get really bad. Exact same thing happens as in my previous example. Actually, I'm just not showing that here. I'm comparing it against a GAM-based method. That's all. But the same thing happens. Okay. So maybe now I'll talk about videos a little bit. Okay. And why this idea of being in infinite dimensions is useful for videos. So the kind of problems I'm generally interested in all kinds of video problems, but the kind of problem I'm going to be interested in today is a conditional problem. So it's a problem where I have a video with maybe some region taken out. So this will be inpainting. And what I want to do is I want to inpaint this in a way that is temporally consistent. Okay, so this is now a conditional problem. All my notation will be unconditional though. I want to make that clear. And all I want to do is, so I want to use an image model. So nothing that has ever seen video data before, only seen images. And I want to make that generate something like this in a temporally consistent way. So there's one extra piece of conditioning here, which is happening. Does anyone know what it is? Well.
You need a robot.
Yeah, why is it the robot? It's exactly what it is. Why is it a robot? So there's actually also text conditioning within this whole framework, which tells you that, which you tell it that it should inpaint the robot. Okay, so two pieces of conditioning, the video and the robot. Okay, and you can also do this for super resolution. Same exact idea. You have some video at a low resolution. You want to actually get out at a higher resolution. How do you do that in a temporally consistent way? Okay, so I do want to show a video of what happens if you don't do this in a temporally consistent way first, which I think is a fun video. Yeah. So this is if I just take each frame and I just apply this diffusion model to it, it would just inpaint a completely different camera because it has no notion of the fact that things have to be similar. And at the very end, it would just inpaint the bench because your region that you need to make gets smaller and smaller and smaller. So now it doesn't even want to put a cat there anymore, right? Okay. Cool. Okay, so how am I going to do this? I'm going to do this with, I'm going to set up an inverse problem, which is going to be a frame-to-frame inverse problem. And what I'm going to assume to know is a deformation. So this in Vision is usually called the optical flow. So this is the idea that if I have two frames that are very close to each other, then I can get the next frame out of the previous one by a simple deformation. So if all my pixels move in some particular way, then that's the next frame. Okay, so this is called an optical flow. It has an issue, of course. So I will fix what's called the frame of vision, which will just be the unit square. And the optical flow here is allowed to take pixels out of this field of vision. Okay, so you can now see why this is starting to become an inverse problem. So here's an example, which I quite like. So you have this mouse, it moves down a little bit on the next frame, and that's precisely what it's doing. So it's taking all these pixels which actually move in this, and it's taking them out, and some completely leave the frame. Okay, so there are many different ways to try and approximate what this mapping T is. Okay, there's PDE-based approaches, there's neural network-based approaches. There's a very large literature within vision as to how one gets at this. This is not going to be my main focus. We just pick a method, and it's a neural network-based method, and we just use that. So we basically assume that these maps T will always be given to us, and I can get at them. Okay, maybe not the best assumption, but it does work in practice sometimes. Okay, so now what is the inverse problem that arises out of this? Okay, so here, maybe I should have said this in the last slide as well. U is my current frame, and U tilde is my previous frame, or at least it's the pixels of the previous frame, which have stayed within the field of vision after I've applied this deformation. Okay, so the prior of this inverse problem is a functional prior on U. And U is my current frame. So I want to get U, and the information I have about it is all the pixels of my previous frame, which have been deformed and which have stayed within the field of vision. Okay, and of course, after which things have been finite dimensionalized as well, right? So this here I'm assuming to be infinite dimensional. This here I'm assuming to be finite dimensional. Okay, and things move by T. Okay, so it's a joint, I'll say, inpainting and super resolution problem. So it's super resolution because T is allowed to move pixels around, and I don't necessarily know how to interpolate well. And it's inpainting because T is allowed to move pixels outside of my frame of vision, and so I need to fill those in. Yeah. Okay. So I will not claim that I'm going to solve this problem in any kind of consistent way. In fact, I think the work that was presented today by Yazid, I want to say, is very much in this direction, is very much in getting maybe more consistent ways of solving this exact problem, given you have a diffusion model prior. And this is, in fact, a linear inverse problem. And it's linear because composition, even though the T is a nonlinear function, on the function space, composition is a linear operator. And so it is a linear inverse problem. Okay, so maybe it fits nicely within the framework. Okay, but I'm going to solve it in a much more simple way. Okay, so this is what I'm going to do. So this is my data. My data now mu are photorealistic images, which I assume to have samples from. I have a map, psi, which is now a map that takes Gaussian noise, puts out an image. Okay, and this map is defined by by a diffusion model. Okay, and it's actually going to be deterministic because I'm going to use the ODE formulation. I said nothing about the ODE formulation because in infinite dimensions, I think, as far as I know, not much is known, but this is what I'll use. And again, I'm going to use noise now, which is trace class. Okay, so covariance, which is trace class. And what I want to essentially have happen is that if I have some noise V and I deform this noise V, then that's the same as if I apply my diffusion model and then deform that instead. Yes. So what I want to have happen is that if I deform the noise appropriately, then I get the same kind of deformation out of my diffusion model. Okay. So this will give me a way now if I sample some noise to deform it in sequence and find and do this basically frame after frame and generate a video. Yeah. So this is the basic idea. So I just have a diffusion model prior, and I want to solve a whole bunch of different inverse problems that are frame by frame. Okay. And the way I generally generate this is through some KL expansion, which is very convenient because it's fast. It's at least n log n, and we can. But this also allows us to be able to manipulate the noise anywhere we want. So that's kind of the key thing. If you sample V in this way, you can manipulate the noise pointwise. It's something you couldn't do if you sampled white noise. Okay, so this is what the functional kind of point of view gives you here. Okay, so I can show you how this is done algorithmically. I have an ODE. Again, I'm using kind of Jackie's formulation of what this would be, except just in an ODE setting. I have no proof that this is a consistent sampler or not, but this is what I'm using in practice. And the inverse problem at each step that I want to solve is precisely this one. So all I've done is I've taken a composition with T on both sides. And the reason this is nice in practice is because you never have to interpolate the output of your diffusion model. So what you say is what you want to match is something that comes out of the diffusion model, interpolated versus what comes out of the diffusion model. Instead of the other way around, if you do that, meaning if I kept the T inverse on the other side, then I'll have to interpolate both. And this is generally not a good thing to do because you get blurriness. Okay. And now all you do is now you can just match this frame by frame by precisely doing this within the time discretization of the ODE. So you say that as you discretize the ODE, you want to match each of the noisy versions of the previous, and you do that by just taking a gradient with respect to them, right? So this term here, is this T, is precisely this term. This term here is precisely this term, which is the previous. It says that because I've made the assumption that if I deform my current frame, I get the next one, then this will be the next one, and this will be the previous one, right? So I can match them up. Okay, and it turns out that if you just do this and you apply this gradient term, this actually works nicely. Okay, so two practical things I want to show. So I'm going to skip this slide because it's useless. Two practical things that I want to show are that one, you can do image generation if you don't use white noise. So you can use noise with a trace class covariance and still get good images. And two, that the method I just showed, which attempts to solve this inverse problem, actually generates temporally consistent videos. Okay, so first one is concerning, can you generate actual images using this? And you can. So this is what the Gaussian. So as you can see, it's quite rough. Kind of this is really a Gaussian random field kind of on the edge of integrability, but it's still integrable and it's still pointwise defined well. And what you can do is basically you can take models that have been pre-trained with white noise, and you can fine-tune them using this noise, and I'll see how well they generate. And this turns out to work very well. So the things, yeah. So there's a whole lot of things here. The two things, the only thing you really maybe should take in is that it has good FID score. So if you believe that FID is a decent metric, then maybe you believe me that fine-tuning this gives me decent images. Okay. Just some examples. So these are conditional. By the way, these are all conditional models that I fine-tune. So one is for inpainting, which I use, and the other one is for super resolution, which I'm not showing examples of here. But this is just an example of the inpainting model. So this is a model which has been fine-tuned with a trace class covariance noise and is able to do this kind of inpainting with kind of arbitrary occlusions. Okay. The next thing is I'll show you videos, but let me just get to the table first. So this table says that we can generate one videos which are temporally consistent, and 2 videos which look good. So the way so maybe we just focus on this two columns. This column is the FID, and it's computed per frame and then averaged. So this is telling you, does each frame actually look good? Does it look like a natural image? And the other one is something called warping error, which essentially tries to calculate how far off you are from the previous frame, so how temporally consistent you actually are. So what you want really is just a smaller number here and a smaller number here. And you can kind of see that if you do what I said, then you kind of get the best of both. So you're not always maybe winning on doing well, but you are still doing, you are still doing relatively well compared to other approaches, but you're also doing very well in terms of how temporally consistent you are. Okay, so it's a balance of having those 2 things. And now I'll show examples. Sorry, so examples are more fun. Okay, so here is maybe I'll show you a few things. Maybe we watch this first. So I do want to show how. So this is a video of just a woman moving through a square, and maybe we can watch how this translates into warping the noise. So here I have some. Make this bigger. I have some optical flow that I've extracted from the previous video, and I've applied it to my Gaussian field, and you can see that you're essentially the woman is moving in the noise. Okay, and that's what it generates. And this is, I believe, a super resolution problem. And I guess this is super resolved version of that video, which still has some flickering artifacts. So it's not perfect, but it is a super evolved version. I think the inpainting examples are maybe a little bit more fun. So you can have this cat, which moves like this, and then we actually get a real cat that doesn't change. So that's pretty good. And the cat doesn't flicker. And maybe I'll show this last one, which is just, again, super resolution. So this is zooming out in a very pixelated video versus if you zoom out in this super evolved version, you can actually read the text, although it becomes nonsense. It does eventually become nonsense, but you can read it. Okay. Okay, so that's it. That's all I wanted to tell you. So we have infinite dimensional diffusion models. Hopefully I have argued to you are important and you should care about them, and they have really good benefits. But I think there's tons of open research. So in terms of getting architectures that work for images that are operator based, I think this is almost nothing done on that. Also, just finishing this theory, just getting necessary and sufficient conditions, I think there's also something not done. The ODE is another thing that's absolutely not done. Unconditional video generation is something we have not done, which I would like to do. Also, how do you, can you use data from both video models and image models to do this better? I don't know. And are there other tasks you can solve? I think there are. So I think there's a lot of really good kind of editing tasks which you can try and attack with this kind of framework. Okay, thank you so much.
Any questions?
Would you be able to sort of extend this method for incorporating in beyond like temporal consistency, like the laws of physics, for example, in the movement of something or that sort of thing?
Yeah, so it's all about how you set up that inverse problem that I showed. So if you can set up a good inverse problem, how you go from the next thing to one thing to the next, and that's kind of a consistent thing that maybe incorporates your physics, then I think you can, though you do need I would say for physics, you would need a proper way of solving that inverse problem, which is something I don't claim to have shown. And so, but maybe some of Eric's work can go in that direction.
Thank you.
Any more questions?
Thank you. Very, very impressive results. Is there any relationship between this map T or the equivariance that you want and the smoothness of the noise that you're using? Or?
Well, not as far as I've considered. So T should be, I've assumed T is injective, and that's all. But I would say that the more and more warping T becomes, kind of the worse things get. And you can imagine why, because you can really make the distribution of the noise, once you apply T to it, look like something you've never seen before, right? If T is very, very warping, then you can make it look nothing like just a drop on the Gaussian.
Yeah.
And the diffusion model will have never seen that. And then it will kind of output nonsense. And so if T is kind of very, very rough, then things are not good.
We have some more time for a question if you want. I have one, actually. So using this, normally the one way to detect fake images or the generated images is looking at the spectra. And you said that if you use a trace class noise, does it actually get rid of this problem? So is it going to be undetectable if you use the right?
Sorry, can you say that again?
So one of the ways people detect generated images is spectra, right? They look at the generated images and their spectrum.
Yes, you can. That's right.
But, and if I'm not mistaken, you said if you use the right noise, right trace class, then you get rid of this problem.
Yeah. You do. So I haven't looked at this on the imaging problem. I've looked at it on simpler problems, and it does get rid of it. Yes.
Okay.
But it should be looked at on the imaging problem.
Yeah. Okay. Thanks. Okay, then let's thank the speaker again.